Welcome to the explainer. So picture this. You're driving down the highway and you pass one of those massive, imposing steel towers carrying thick power lines across the countryside. Have you ever actually wondered, why do they need to be so huge? Like, why are we transmitting power at such incredibly high voltages instead of just, the standard voltage that comes out of your wall at home? Well, today we're demystifying the physics and the economics behind high voltage power transmission. We're going to break down exactly how it works and why our entire modern connected world completely depends on it. Okay, let's dive right into this with a bit of a thought experiment. What if transmitting power actually cost more energy than you generated in the first place? Imagine you're running this massive power plant, you're spinning a huge turbine, only to find out that the sheer act of pushing that electricity out to a distant city consumes all the energy you just made, and then some. It sounds like a totally catastrophic, impossible scenario, right? Like, why would anyone ever build a system like that? But mathematically, if we aren't incredibly careful with how we design our electrical grid, this is exactly the trap we fall into. Just consider this staggering number for a second: 825.9 megawatts. If you tried to send just 100 megawatts of power, which, by the way, is roughly enough to run a small city, over a standard 11 kilovolt line over a long distance, the resistance in the wires would generate massive amounts of heat. How much? You'd lose 825.9 megawatts entirely to heat and waste. Think about that. You're trying to deliver 100, but you're losing over 800 along the way. At that point, you aren't powering a city. You've basically just built the world's largest, most expensive toaster. The transmission wires would literally melt down before the power ever got anywhere near its destination. When you actually run the numbers on this scenario, the real culprit becomes super clear. To deliver that 100 megawatts at a relatively low 11 kilovolts, the electrical current has to absolutely skyrocket to over 5,000 amps. And since power loss through wire resistance relies heavily on the amount of current flowing through it, we end up with that massive 825.9 megawatt loss. It's wild. This proves that low-voltage transmission for long distances isn't just a little inefficient. It's literally impossible. It fails spectacularly. Now, what's really interesting about this is the fix. The elegant solution to this massive problem lies in a fundamental law of physics. For a constant amount of power, current is inversely proportional to voltage. It's a bit of a mouthful, but basically, as we boost the voltage up, the current automatically shrinks down. Higher voltage directly results in lower current. It's a remarkably simple relationship, but I'm not exaggerating when I say it is the absolute bedrock of our global electrical grid. So why the obsession with shrinking the current? Well, it all comes back to the power loss formula. Power loss in those conductors equals 3 times the current squared times the resistance. The magic word there is absolutely squared. The losses depend on the square of the current. This means that reducing the current doesn't just reduce your energy losses linearly or by a little bit. It has a massive exponential effect on saving energy across the entire length of the lines. And this brilliantly illustrates what we can call the 100x rule. If we increase the voltage by a factor of 10, the current drops to just 1/10 of what it was. But because of that squared relationship we just talked about, your power loss drops to 1/100th. A mere 10 times increase in voltage slashes your energy waste by a factor of 100. That is an absolutely incredible return on investment from a pure physics standpoint. Let's actually look at this in action with a direct comparison, because this is the ultimate aha moment. Both scenarios here are transmitting the exact same 100 megawatts. But on the right side, we've stepped the voltage up 10 times, moving from 11 kilovolts to 110 kilovolts. As a result, the current drops from over 5,000 amps down to just 525 amps. And the loss? It plummets from that catastrophic 825.9 megawatts down to a highly manageable 8.27 megawatts. Boom. By simply turning up the voltage, we transformed an impossible system into a highly efficient one. So the crucial point here is that this physics hack doesn't just save power, it saves cold, hard cash. It saves materials, it saves real estate. This brings us right to benefit one, a drastic reduction in conductor size. Because the high voltage lines are carrying so much less current, the wires themselves don't need to be nearly as thick. We can use a much smaller cross-sectional area for the conductor. This saves absolute tons of expensive metals like aluminum and copper, drastically cutting down the material and construction costs of building the grid in the first place.
Which leads us seamlessly into benefit 2, the economical transmission of bulk power. Think about it. Generating stations are rarely right next door to where the power is actually consumed. We build giant hydro dams up in remote mountains or massive wind and solar farms out in wide-open deserts. This high-voltage trick is literally the only way it becomes economically feasible to pack up all that bulk power and transport it over hundreds of miles to the major load centers, our cities, with acceptable, minimal losses.
Naturally, less power lost along the way means benefit 3, greatly improved transmission efficiency. Efficiency is simply the power delivered to the destination divided by the power originally transmitted. When we drastically shrink those line losses using high voltage, the top number stays very, very close to the bottom number. It just reinforces that managing voltage is really all about maximizing the overall efficiency of our entire power delivery infrastructure. But wait, there's actually more to it. Benefit 4 is a reduced voltage drop. As power travels down a long wire, the current interacting with the line's natural impedance, basically its internal resistance, causes the voltage to gradually sag. By using high transmission voltages to keep the current as tiny as possible right from the start, we minimize the sagging effect. This makes sure that by the time the electricity finally hits the receiving substations near your local neighborhood, the voltage remains stable, suitable, and ready to be safely stepped down for everyday use. And then we have benefit 5, which focuses on getting the absolute most out of the infrastructure we've already built, better utilization of our transmission lines. Let's face it, acquiring land and building new transmission corridors is incredibly difficult, heavily regulated, and seriously expensive. High-voltage technology allows an existing physical line to carry a vastly larger amount of power without overheating the wires or pushing the system past its stability limits. It maximizes the capacity of the footprint we already have. Let's zoom out for a second and see how this builds into the big picture. All of these physics principles and economic benefits culminate in one massive, world-changing achievement: the modern interconnected power system. High-voltage networks allow us to string together wildly different generating stations and load centers across entire continents. It transforms isolated local power plants into one giant, resilient continental machine. Because we can tie everything together with high voltage, we unlock these 5 incredible secondary benefits. We can share generation between regions, meaning, hey, if one state has a cloudy day, no problem, they can borrow solar power from a sunny state right next door. It dramatically improves reliability, keeping the lights on when local plants fail. It effortlessly supports load growth as our cities expand. It provides alternative power flow paths around storm-damaged lines, and it allows for significantly better utilization of our diverse generating resources across the board. This interconnection is literally what makes modern daily life function securely. Which brings us to our final takeaway. As we look towards the future of energy, I want you to ask yourself this: how could we ever transition to distant renewable energy sources, like large hydro dams, offshore wind, or massive desert solar arrays, without this foundational high-voltage principle? Well, the truth is, we couldn't. Those massive transmission towers aren't just steel eyesores. They are the high-voltage highways making the entire green energy transition possible. They're the unseen key to connecting our growing cities with a clean energy future. Thanks for joining me on this explainer. And remember to always keep questioning how the incredible world around you actually works.